Welcome back to this course on tribology. This Today's lecture is on engineering surfaces. Now, engineering surfaces is an important issue in tribology because the two loss outputs in an engineering tribological system are friction and wear. And both these occurs at the interface between the two sliding surfaces. Therefore, the surface characteristics, their topography, their nature are very important in understanding the tribology. So today, we'll look at the engineering surfaces. Just before we go to the main pages, just to give a brief understanding, look at this picture. There are two surfaces. One is a blue surface, other is a red surface. I think the first thing one should know is that the engineering surfaces, or for that matter, any natural surfaces, are never absolutely smooth. And therefore, when the two surfaces come in contact, they do not meet in all points. They meet only on the peaks of the asperities or peak of the hills. And therefore, the real contact is different from what we see. Okay, so with this introduction, we'll go to the main pages. Now, first thing we understand that all surfaces are rough to some extent. They may be the engineering surfaces which are machined or manufactured by some engineering machinery, or in natural surfaces. As I say, they are never smooth. They will always be rough to some extent. One of the most the smoothest surface that we can find in nature is a mica sheet. Even this is not absolutely smooth, and it is also rough to an atomic scale. So here we must differentiate between the real area of contact and the apparent area of contact. One of the easiest example that a teacher has in his class room is a duster and a table. So if we put the duster on the wooden side on the table, then we see a contact between the duster and the table. And if the duster is a 10 centimeter by 4 centimeter, we say that the contact area is 40 centimeters square. But that is absolutely wrong. That is because the surface of the table and the surface of the duster both are not absolutely smooth, and hence the contact occurs only at the tips of the asperities or the peaks, and hence we have a difference between the real area of contact and the apparent area of contact. Look at this picture at the bottom of this page. You will see that the two surfaces are in contact, and as the surfaces are pressed together, there will be areas of contacts. So here in this picture, we have got three areas of contact, A1, A2, and A3. So these are the real areas of contact, and the apparent area of contact is A. So one can see very easily that the real area of contact is a very minor fraction of the apparent area of contact. And this is one of the biggest cause of the tribological loss outputs, namely friction wear. And we'll see that a little later. But for the time being, let us try to understand the surfaces. Roughness on an engineering surfaces are due to machining or manufacturing processes that we know. And depending on the manufacturing processes, there are different orders of surface roughness. So let us look at those orders. Firstly, the first order roughness, surface roughness, is due to the irregularities arising out of the inaccuracy in the machine tool or out of the deformation of the workpiece under the cutting forces and under the weight of the material. Now let me explain this to you. If you look at this picture, you will see a single point cutting tool being a bar, and there cutting forces are generated in X, Y, and Z direction. And there is also the weight of the workpiece itself. And these things together make some irregularities in the cutting process, and hence the surfaces we get will not be smooth. So the irregularity is due to the cutting forces and the deformation out of the cutting forces and the weight are known as first order surface roughness. Second order surface roughness, irregularities caused by vibration of any kind, for example, chatter marks. So when a machining is in progress, there will always be some vibration because the workpiece and the tool post both are not absolutely rigidly held. There will be some deformation, and due to the machining process, there will be some vibration. This vibration will induce some arbitrary irregularities in the surface during the manufacturing process. So the irregularities due to vibration is known as second order surface roughness. Then the third order surface roughness. Irregularity is caused by machining itself. When we machine by a single point cutting tool, normally we produce a periodic roughness because it is cutting in some sort of spiral mode. So we get either a sine or a cosine function. And this will be there even if everything is perfect. There is no vibration, machines and machine tools, everything is perfect. Even then, there will be a third order irregularities, and this is the main roughness that we get. And usually, for a single point cutting tool, it will be periodic like so. If we a grinding wheel or some such other sort of machine tool, then the roughness will be random or non-periodic in a way. The fourth order surface roughness is caused by the rupture of the material. As we go on machining, the machine tool takes away the material, and the material will come out as a chip form. And the chip has to rupture some point. Where the rupture, it causes some irregularity surface. And this kind of irregularity is called fourth order. So let me summarize this. There are usually 4 orders of surface roughness due to machining. First order is due to the inaccuracy in the machine tool and the workpiece load and work forces. Second order is due to vibration. Third order is due to the machining itself. And the fourth order is due to the chip formation or the rupture of the chips. I think out of these, the third order roughness is the most important one, and the other ones, other type of roughness will be superimposed on this. We'll see this later on. So we go by the machining process and we'll see what kind of roughness we get. Now we try to quantify the roughness. You see, when we say that this surface is rough and this surface is smooth, it is a very qualitative description, and it really doesn't make much sense to study. But anyway, there are a number of parameters developed to describe the surface. The first one is valley to peak to valley height. As we discussed earlier, there will be peaks and valleys in the surface due to machining, and the total distance between the peak and the valley is called R max. But let me tell you very clearly that this parameter is not of much use. You can have many surfaces with the same R max, but of different nature. Suppose if the valleys and the peaks are closer together or far apart, then the surface will be different, but you'll have the same R max. So this is a very simple and basic definition of roughness, and it is not of much use, except to describe a surface semi-qualitatively. Now, next comes the centerline average. The centerline average is quite widely used in shop floor because it's an easy way of giving the arithmetic average of the departure of the surfaces, surface heights from the mean. So what we do here is we take the height of the surface y, which is a function of x. So y is a function of x. Y dx is integrated over the sampling length, say L, 0 to L, and we divide it by the sampling length L. So what we do is we find out the total area enclosed by the surface and the mean line and divide it by the sampling length. So this gives us some kind of a arithmetic average. Again, this can be either given in an integral form as 1 by L integral 0 to L y dx, or we can also look at it in a simpler way by adding the areas A1, A2, A3 to A7 in this picture divided by L. So this is simply adding up all the areas and divided by the L. And that's what we have done in the integrated form also. So this is an arithmetic average, but again, this is not a complete description of the surface because it doesn't take care of the frequency variation. You can have many surfaces with the same CLA, but with a different frequency variation. Then comes the root mean square value, RMS. This is also used quite widely in industry. And here we take the geometric average. So we take the ordinate as shown in the picture, ordinate y, and we square it, and we say integral of y squared dx is 0 to L, and divide by L, some sampling length, and take the square root of this. Now this definition is useful because this takes care of to some extent, the distribution of the surface. So this is more sensitive than CLA. Now there are many more parameters, and another parameter is bearing area curve, or widely known as about and Firestone bearing area curve. Let us look at a surface as shown in the picture here. So this is a surface, and the expression bearing area simply means how much area is available for bearing the load, basically. Suppose we bring this flat surface slowly over this rough surface. Then what will happen is initially the topmost peak will be in contact, and then as it goes down and down, then more and more surfaces will be in contact, more peaks will also be in contact, and the area available for bearing the load will be more. So let's look at the variation of the void volume and the material volume. As we go down from the maximum height, say this is the maximum height of the peak, go down, the material, this is the material, this is material, is increasing. Total material available is increasing, and at the mean, there is a crossing point, and then it goes down, and here it comes to an end. So this x coordinate in this picture gives you the bearing area percentage. So as we go down, the bearing area is 0 at the beginning, and then it is increasing, and it becomes 100% as we go down to the end of the value of the bottom of the lowest value. So this is the one. So this bearing area curve was quite widely used at some time, not very much used these days, but this is a very useful parameter because it tells you at a site that how much area is available for taking the load. Now we come to some statistical parameters that are used in industry also. Mean value. Mean value is very similar to what we have called CLA. Again, that is nothing but if we describe the surface as a function of x, y is the ordinate, y is a function of x, then we integrate y dx from 0 to x, x being the sampling length, and in the limit, x tends to infinity. So ideally, it should be a very large sampling length, and then we divide it by that length, and we get a mean value. Mean value, as we have described before, is the mean line is such that the area above is equal to the area below, enclosed by the surface and the mean line. There are certain methods of finding it, but here we look at it from the ordinate point of view, the surface is given by a string of numbers, which are the variation of ordinates y. And this is why it is y dx 0 to x, 1 by x, in the limit x tends to infinity. Then we have mean square value. Mean square value is also another statistical parameter. Here, instead of y, we take y squared dx, because this has got some implication of the distribution. So here we do the same thing, except we integrate y squared dx 0 to x, 1 by x, in the limit x tends to infinity. But this itself is of not much useful in surface roughness point of view, or even signal analysis point of view. We normally take this root mean square. We take the root of this, and this is useful. Now, the root mean square value that I've shown here is with respect to some mean value. If we take mean as 0, then this will be a 0 mean root mean square value, because the mean may be computed with reference to some other reference as shown here, or the mean line itself can be the reference. So if we take the mean line itself as a reference, then this mu will be 0, and it will be simply integral y squared dx 0 to x and 1 by x in the limit x tends to infinity. So this is the root mean square value with reference to some other coordinate. This root mean square value is basically the same as the standard deviation. And this is a well-known parameter that is used all over. So root mean square value is basically the same as the standard deviation, although there may be slight differences in certain areas of computation. But for this case, we'll consider root mean square value same as the standard deviation. So in this page, we have same varying area curve, first introduced by Abbott and Firestone, which gives us the area available for bearing the load, mean value, which is similar to the CLA, root mean square value, which is same as the RMS value, RMS surface reference, and standard deviation, which is the deviation or standard deviation of the heights of the surface from either from the mean itself or from with reference to some other coordinate system. Then we go to probability density function. Now, this is an important parameter used in surface roughness characterization, also in many signal analysis. If we look at a surface, say this surface, which is a y as a function of x. Now, probability of this function lying between a window of y and dy, if this is y, and y plus dy. So a window of dy is the probability. And probability of finding this function in this window, and we compute this by adding up those components like delta x1, delta x2, delta x3, delta x4, and so on, and divide it by the total sampling length. This is the probability. So that is not very difficult to understand. The probability of finding a function within a window of dy at a distance of y from the mean line or the reference line is the, in the limit x tends to infinity, xy by x, xy being the sum of the amount of the function lying between the window. Now the probability density function is defined as 1 by x, xy by delta y, in the limit delta y tends to 0 and x tends to infinity. So probability is in the limit x tends to infinity, xy by x, but probability density function is 1 by x, xy by delta y in the limit delta y tends to 0 and x tends to infinity. So this is a very important parameter in characterizing surface roughness and many signals in signal analysis processes. In fact, roughness itself can be thought of as a signal, because when we measure the roughness, we take a piezoelectric crystal and move it over the surface and take the signal from it, and that is plotted as a roughness. And remember, this is only a line, a particular section of the surface. So this is also a signal analysis, and this is useful in our roughness characterization, also in signal analysis. Now, if we look at the probability of the function lying between the two values of y1 and y2, it will simply be py dy, py being the probability density function integrated between y1 to y2. Now, if we look at a function, either Gaussian or even non-Gaussian, Gaussian will be only for the completely random surface, and we integrate this probability density function with dy between minus infinity to plus infinity. And the answer is simple. The answer will be certainty. So it will be 1. Probability of finding the function between minus infinity to plus infinity would be a certainty, and it will be 1. So the probability of finding the function between y1 to y2 would be the hatched portion of this curve, and the probability of finding the function between the two extremes would be 1. Now, let us look at the practical application of this function in engineering practices. When we produce surfaces by machining of different kinds, we may get a periodic function by a single point cutting tool, as we have discussed earlier, which looks something like this in this figure. So here it's a periodic function with the maximum value from the mean is y max, and the minimum value will be minus y max. Now, what would be the probability density function of this curve? The simple way of finding this is to look at the slope of this curve. Slope of this curve, where it crosses the mean line, is maximum. It's quite simple to understand because the slope is 0 here and slope is 0 here, so it must be maximum here. And hence, the probability density function, without doing any mathematical calculation, we can say would be minimum at the mean point. So if we take the y max and y mean, the two ends, and plot the probability density function, then we'll see that it is minimum. So it will be something like this. And this can be achieved very simply by looking at the definition of probability density function and integrating it. So this is a useful way of defining a periodic function obtained in machining process. Now, if we look at a random profile, which is usually generated by grinding process or lapping or using grits to roughen the surface, which is often used roughly, they usually give a random surface. And we all know that the random surface is given by a Gaussian distribution, which is something like this, which is there's a peak at the middle point and it widens on other two ends. It is usually given as py 1 by sigma root 2 pi e to the power minus y square by 2 sigma square. Sigma is the standard deviation. Here, sigma, although is same as RMS, we write it as a standard deviation because that is the usual definition of Gaussian distribution. So we now get a probability density function for a purely random surface or zero mean. This is called zero mean Gaussian surface. Mean is at the 0 point and it will be widening on both ends. Now we take a surface which is a periodic function but a random distribution is superimposed on the periodic function. Look at this surface. It is a periodic function, but a random signal is superimposed on this. So this will obviously be a combination of the other two distributions that we have got. Let me look at this. This is a Gaussian distribution and this is a periodic distribution. So we combine these two and we get a probability density function, something like this. And this may be obtained very easily by doing the integration given the function. So this gives us a method of identifying the surfaces from the probability density function. Now, we look at the probability density function of Gaussian distribution, as we have said, is given by 1 by sigma root 2 pi e to the power minus y square by 2 sigma square. This is true if it is a zero mean. That means if it is around the zero, the mean, about the mean. But if we take with reference to some other point, say at a distance of m from the zero, then we have to write it as y minus m square. So this is a non-zero mean Gaussian. So this has to be remembered that there may be a zero mean Gaussian and non-zero mean Gaussian, depending on what coordinate we are choosing. Now we go to some other parameters which are very common to use in line with the probability density function. That is the skewness. The skewness is nothing but the departure of the distribution curve from the symmetry. This is the symmetrical distribution. But if it departs, that means if it moves either to the right or to the left, then we call it positive skew or negative skew. Now, what does it mean? A normal distribution, the activity is condensed at the central zone. But if it is skewed on the right, then the activity will be condensed on some other zone. So if the activity is condensed here on the right zone, then there will be right skew, and if the activity is skewed to the left skew. To give an example, let's take the heights of the students in a class. If there are more tall students and a few short ones, then the distribution will be positively skewed. And there are many such examples. So it simply gives the departure of the distribution from the symmetry. If it is not symmetrical, then it may be either positively skewed or negatively skewed. Similar to this, there's another, one more point about skewness. This is basically a third moment, y cube, third moment of the density, probability density. Similarly, we have a fourth moment, which is called kurtosis, which simply gives a measure of peakedness. That means how peak the distribution is. If the distribution is Gaussian, that means peak is greater than 3, then it will be high peak. And for low peak, k is less than 3. Now let us try to understand what it all means. It simply means that if the peak is concentrated, if the data values are concentrated around the mean, then the peak is Gaussian. But if the data values are concentrated somewhere else or less concentrated, then we call it low peak or high peak. So the peakedness is in a data distribution is the degree to which the data values are concentrated around the mean. If they are not concentrated around the mean, then the peakedness can be more or peakedness can be less. So this is the thing to remember, that if the peakedness in a data distribution is the degree to which the data values are concentrated around the mean. Okay. So these two are very well-known parameters used in collaboration used in we go to the function. Now this is again a very useful parameter, and again I say widely used in both surface roughness characterization as well as in signal analysis. It is simply the departure of the values of a data at one point, say here, from another point here, the distance of tau. So we have a function tau yx like this, and we want to find out how correlated the function is between 2 points separated by a distance tau. Now this is usually done by multiplying the two functions at the two different points yx and yx plus tau with respect to dx, and integrating over the whole sampling length x and dividing by 1x and dividing by x, and assuming that x is tending to infinity. That is very broad sampling length. So R tau is the autocorrelation function. It's defined as limit x tends to infinity 1 by x integral 0 to x yx into yx plus tau dx. So obviously, if tau is 0, function become equal, and they are perfectly correlated, and there our tau is maximum. So we can say that R0 is always greater or equal to R tau for all values of tau. If tau is not 0, then there will be less than R0. Okay, so this is one thing to remember, that if tau is 0, autocorrelation function is maximum. Now again here we try to look at some of the applications of this function in our daily use. Again, let us take the three examples that we have taken before, that is sinusoidal surface roughness, random surface roughness, and sinusoidal surface roughness with superimposed random roughness. So if we take a sinusoidal surface roughness, if we do the calculation, it can be seen that it simply becomes a cosinusoidal it becomes cosine. Okay, so this is a simple way of defining a surface roughness in terms of autocorrelation function. A sinusoidal roughness will give a autocorrelation function which is of cosine function. Okay, so that is very simple. Let's go to the next one, which is a random surface roughness. Now the random surface roughness again can be shown to start with a high peak and then slowly coming down to and settle down to a mean value. So it decays to a mean value very quickly from a very high peak. So this is the nature of the autocorrelation function. So if we get an autocorrelation function of the signal or the reference, which starts with a very high value and then settles down or rapidly decays, then we can declare that the surface to be random. So this is one way of characterizing the surface roughness. Now, if we have a surface which is sinusoidal superimposed with random roughness, which we have seen it with respect to the probability density function, as shown here on the reference side, then we'll see that the autocorrelation function starts with a high peak and then it settles down to a periodic function. So this is a very useful information. If we can find out the autocorrelation function of the signal and gives like this, then we can assume that it's a sinusoidal surface with a superimposed random roughness. One example could be a single point cutting tool producing a sinusoidal surface with a chatter mark, which can be of a random nature. And then we'll get a surface which is sinusoidal with a superimposed random roughness. So if we get an autocorrelation function like this, then we can see that we can say that the roughness is of this order. So these are the ways of correlating or using these functions for our daily applications. Now we look at 3D surface roughness parameters. Now, till now, whatever we have seen is a 2D surface roughness. Now, surfaces are never 2D. This is a real surface. So what we have done is we have simply taken a section and assumed that the section is a typical section like this. And we have looked at the profile of that section. But ideally, we should look at the total surface. So there has to be some parameters to define or to describe the real surface. And there are many parameters designed or derived. One of them is arithmetic deviation of surface topography, SA. SA is because a surface, which is something very close to CLA, where we take the function y as a function of x and we dx and integrate it between over the whole sample. Here we do the same thing, except that we take a surface which is a function of x and y both, and we integrate it over dx and dy over the sampling length, Lx and Ly. And this in the digital form can be written like this. So this is not very difficult to understand. This is very similar to our CLA, except that it takes care of the deviation in both x and y direction. There is also another very widely used parameter called 10-point height, SZ. This is defined as, or it represents the average value of the heights of 5 highest peak and depths of 5 deepest valley points within a sampling area. So it simply takes the sum of the heights of the highest peaks and some of the depths of the valleys and add them and take 1/5. It's a very simple way of doing it. So eta pi and eta vi are simply height of the peak of ith peak, and eta vi is the height of the ith valley. So we simply take the heights of the 5 highest peaks and this one, and 5 deepest valleys, and add them and take 1/5. So this is one way of taking a 10-point average. This is useful in defining the 3D surface. Again, there are summit density of surface. There are many summits. Summits means peaks. So how is the summit defined? Summit is the highest point. If you compare the ordinates, say 8 or 10 ordinates around, and find that the certain ordinate is the highest, then that is declared as the summit. So summit density of a surface is nothing but the number of summit in a sampling area. Very simple. So NS is the sampling, is the number of summits. As I said, summit is defined as the highest point around 10 or more peaks around. So summit, number of summits divided by the area, and that can be given in the digital form like this, where we can say with respect to the previous definition that Lx is nothing but delta xn and Ly is delta yn. Delta x, delta y are the sampling distances. Now, these are the few of many 3D surface roughness parameters available. So we'll not go into the details of all this, but I'll mention a few of them. Again, we need to find out the skewness and kurtosis of surface height distributions over the 3D surface bearing index, core fluid retention index. That is important in lubrication, either the full fluid lubrication or mixed fluid lubrication. And the valley fluid retention index, very important parameter. RMS slope of the surface. The surfaces will have slopes. So root mean square value of that is an useful guidance in characterizing the surface. And then the mean summit curvature. Summit curvature is also a very important point because that will tell you how the surface will meet and slide with respect to another surface. So these are the few more 3D surface roughness, and with this we call it a day today. We'll go for more tribological details in the next class.